Alright, hell yeah. So we have dynamics, and we're going to solve this problem like not how they want us to. You know what I mean? Because sometimes you get like a hard problem, and you're like, I don't know how they want me to solve it. So I'm just going to solve it kind of the way I do a lot of problems like this. It is pretty cool. So this thing is just spinning at a constant angular velocity. And they want to know at this moment, hey, what do they want to know? They want to know the angular velocity of this bar. Okay, so what we're going to do is we're just going to run this for just a fraction of a second. We're going to have, as this wheel rolls, and is it rolling about a fixed pivot? The wheel rolls without slipping with a constant clockwise angular velocity. No, so I guess it just rolls without slipping. So it actually is going that direction. Oh, I don't know if I actually will be able to include that, but no, I think we're good. Okay, so what I do is just, if we run this just for a little bit, more or less, like if this thing is just going to go up just a tiny bit, and almost straight up. You know what I mean? Any part of this thing out here is going to go straight up. Alright, hell yeah. So we have dynamics, and man, I thought I was just going to solve this one with a kind of a cool method of just like, hey, let's just run this thing just for a split second. But man, I thought it was on like a wheel. I mean, I thought it was on a pivot, but no, this thing's rolling. So that adds so much dimension to it. So this thing's going at 1.6 radians per second. Anytime you see the word radian, just be like, what the hell is a radian? And so we're going to go from this angle, and we're going to say 60 degrees. So that's going to be 1 radian. Another 60 is 2. And basically there's going to be 6 of these radians in a circle. Okay, and so this is 1 radian of angle. And then so this is 2. So 1.6 is right there. What I'm getting at is I just want to run this for like, what? Should I run it for 1/10 of a second? Well, if I ran it for 1/10 of a second, this would be, break this up into 10. So we're going to go 1, 2, 3, 4, 5. Okay, so if I ran this for 1/10 of a second, we would be right there. But because this rolls without slipping, whatever the tangential distance goes, if you just pretend like it is on a fixed pivot and it's moving with this angular speed, if we go that far, if that's going to be our angle change in 1/10 of a second, this distance right here, s, and let's get some equations. I'd never do this, and I think, yeah, so this is, because even the arc length equation, I don't think is super intuitive. I get to it saying, hey, this is the angle in radians, and so I have, there's a few things that are radians. So angle is in radians, omega is in radians per second, and angular acceleration is in radians per second squared. Okay, so I'm going to say, and I just do like the axiom that, hey, multiply these by a radius, and you get something normal. This one becomes arc length, this one becomes tangential velocity, and this becomes just acceleration. Cool, so let's do this. So we're going to have the angle in radians times radius, maybe we can just call that r, is going to equal arc length. Sweet. Because even just doing it like this, I don't know. Whoa. See, I don't even have this down. Yeah, I don't know. You know what I mean? I don't know. That this equation is just not super intuitive, but I just use the, hey, radians times radius is something normal. And I can go the other direction too. If I say, hey, if I got something normal, what do I do to it? Well, we got to do something odd. You know what I mean? So we got to divide by radius. I don't even know what that means, but hell yeah. I get radians. So that's going to be my little axiom. If I have angular, or if I just have acceleration, maybe tangential acceleration. Yeah, this is tangential. And I want to get angular acceleration. What do I got to do to this? Well, this is something normal. Let's do something odd to it. And hell yeah. So there you go. So, and then in the reverse is like, hey, if I have radians per second squared, I got radians, that's weird. I need to multiply by the radius to get something normal, and I get tangential. Perfect. Alright, so that was just a little tutorial on radians. It's not very proofy, it's just, hey, this is just kind of the little axioms I use, so I know what the hell's going on. Okay, so, yeah, which one are we going to use? Yeah, we're going to use this theta times r is equal to arc length. And so, now what? Holy Toledo, you know what I mean? So sometimes, yes, this is where angular stuff shouldn't be very hard, but it is just because you're using weird terms. We all know, so I just go back to like velocity. So if I say velocity is all about like miles per hour, you know, if you're driving in a car, meters per second, but at least it's something normal. And then you have some, you know what I mean, hey, maybe you're going miles per hour for like an hour. You're going to go 60 miles per hour for 1 hour. Cool, you're going 60 miles. And so these three things are related. You know what I mean? Velocity, time. So if I just did that, velocity times time is equal to distance. Or I can take, hey, I'm going 60 miles and I'm going 60 miles per hour. So this is going to be in miles and this is going to be miles per hour. So that's the same thing as saying miles or meters and then dividing by meters per second. So I kind of use this idea that the units are the equation. So if we go back to here, what do we have? We have radians per second. So we have, hey, unit of time maybe. And then a unit of probably distance. Well, radians per second. Well, how would it? Yeah, this is kind of interesting. Oh, yeah, because radians is dimensionless. So you actually have to get tangential velocity. So you have to go radians per second times radius in meters. And then this is going to be radians times radius is equal to tangential velocity. So then we got meters per second. Okay, cool. So I guess, and then once we got tangential velocity, yeah, then we can use, we can rearrange these three terms any way we want to. Cool. So what's the tangential velocity? Yeah, so let's do that. So again, velocity tangential is something normal. That's going to be something odd divided by the radius. Oh, no. Yeah, holy hell. My axiom is just getting all messed up. So we're going to say radians, 1.6 radians per second times radius. Radians times radius is tangential velocity. The radius for this is going to be, what, 0.4. So I'm just going to say 0.4 meters. That's 400 millimeters. That's taking 400 divided by 1,000. Sweet. So we have 1.6 times 0.4. And I don't know what that is. So we have 0.64 meters per second. Alright, sweet. So now we know our tangential velocity. We're going 0.64 meters in 1 second. And hopefully, let's get some idea of what size this is. Because if this is 0.4 meters, I know that a meter is 40 inches. That's probably the best, SI to American that you could probably get. That little, So half of that's going to be 20. I don't know what 0.4 is, but I know what a tenth of 40 is. That's going to be 4 inches. So if I got 4 of those, hey, this is going to be 16 inches. So we have a radius of 16 inches and then a diameter of 32 inches. Just kind of for some perspective. And then we would have a circumference, if we have 0.8, we multiply by 3, this is going to be our circumference, about 2.4 meters. And I guess 32 times 3, that's going to be 96 inches. Okay, So that's 8 feet. I know that from a 2x4. So yeah, so we have 8 feet in circumference. And we're going, if this is 8 feet, we're going about, this is 4 feet. Hey, we're going about 3 feet per second. Cool. Is that even right? We're going, tangential velocity is 0.64 meters per second. How many feet is that? 0.64 meters per second. So I'm gonna do 1 meter is 1,000 millimeters, and then 50 oh, I'm really tired right now. Holy hell! 1 inch. Okay, so and then multiply 12 inches by a foot. So we got 0.64 times 1,000 divided by 25.4 divided by 12. Okay, so it's only like 2 feet per second. But didn't we think this was okay, whatever. Well, I guess there's 2 pi radians in a circle divided by 1.6. I don't even know what we're doing right now. Holy Toledo. Okay, so what are we doing? So we're getting our tangential velocity, and so yeah, we have that, and we're just going to multiply it by 1/10 of a second. So we got 0.64 meters per second, and we're going to multiply it by 0.1 seconds. Seconds are going to cancel, and we're going to get 0.064 meters, and we do this, that's going to be 64 millimeters. All right, hell yeah. So this is going to go up. Oh yeah, the whole reason we were doing this is because whatever this distance travels, our arc length, is this origin is going to travel this way. So this whole center is going to travel 0.064 meters that way. And let's do everything in millimeters. Holy hell. So we got 64 millimeters that way. And then, but we do, but now we are at this angle. You know what I mean? So everything that was on this line is now up here. Alright, this is brutal. Oh yeah, holy Toledo. Yeah, it always seems like you have 2 different things that are the radius, but you have to kind of forget about this bottom one and say when you roll it up here, you're going to have kind of this angle, and that comes down. So sure, this would have been your extra radius, but you are sweeping that angle, so this is your radius. And what we're interested in, we were right here, you know what I mean? So at this point, and then when we sweep it up to here, if this point was up here, you know what I mean? We're kind of figuring that one first, and then we can just say, hey, so if we go up by this amount and then over by this amount, this point that was at the halfway mark, we'll just go over by half of this. So whatever this distance is, maybe we'll call this x and y. This is just going to be x divided by 2 and then y divided by 2. Okay, so how would we find this? Well, we need to know the angle, and it's totally spelled out. So radians per second times 0.1 second, or 1.6 radians per second times 1.6 radian. Oh, holy hell! So we got 1.6 radians per second times 0.1 seconds. This gives us 0.16 radians. Now, just for the conversion, because no one knows what the hell radians are, but if we divide by 2 pi radians, that's how many radians are in a circle, which is 360 degrees. Now we can see that. Let's see what angle that is. times 360 divided by 2 divided by pi. Alright, so that's 9 degrees, 9.16. So, and we could have, if we want a more accurate answer, we can run this for a 100th of a second. And then get this. But I'm gonna, let's see. I'm gonna work in well, I don't know. Yeah, let's work in degrees. So I'm gonna store this as 9.16 degrees, theta in my calculator. And now what, and then, so this is my hypotenuse. So now, hey, the sun is shining on the sinus, so we have y is equal to r sine theta. It's going to be the hypotenuse, the larger number, and then times that fraction. Sines and cosines are fractions of this. Cool. And sine of a really small number, I don't know. Well, yes. Well, we can even guess this. That's kind of my style. It's like, hey, if you're gonna do anything in your calculator, try to guess. The cool thing about using radians, because, hey, what did we say? It's going to be 0.16 radians. Well, radians, like radians times the radius does give you the arc length, which is really close to the actual distance right here. Because if your angle is small, this arc length and this are the same. So basically, this is kind of cool. It's saying S is equal to Y, and yeah, it's just a function of how radians are kind of unique in that way. If you did diameters, hell no. Then your arc length is going to sweep out, I think, twice or something, and it's not going to be this nice little thing. But anyway, so yeah, so we know that, hey, this y is approximately just 0.16. Cool. So now when we do this, oh damn it. No, it's 0.16 times the radius, which is 400. So we have 6. Yeah, I'm sorry. I know it's like 6. What is it? 64? Is that what we're saying? Yeah, we don't have to do that twice. So 64, 2 zeros, and then do that. So cool. So we're at 64 millimeters. So y is approximately 64 millimeters. Now, if we do it right down here, we're going to say we have 400 millimeters times sine of 9.16. So we have 400 sine of theta, and we get 63.72 millimeters. All right, why is there such a discrepancy there? Oh man, I'm just really tired right now. I don't know. I thought this was like 46 or something. But anyway, no. 64 and 63.72, obviously those are really close. So yeah. So there you go. Oh man, this is awful. But yeah, we're doing it. You know what I mean? Maybe this video is just like, holy hell. Like when you just have no more energy, can you do anything? It's a lot harder and you're going to make a lot more mistakes. Okay, so we did that one. Now let's do this cosine one. Now the cosine is just going to give us this length. We actually want x. So I mean, sometimes it's good to just like do one step at a time. Be like, hey, let's take the cosine of this, get that, and then what? You know what I mean? Well, we knew that this whole thing was the radius. So x is just going to be like, hey, the radius minus what we got. So if we just want a formula for x, all right, we're back. So if we just want a formula for x, that's just r minus cosine theta. And this little formula comes up hella in trigonometry. So anywhere where you see an equation, just know that they're doing kind of this. You just want that smaller quantity. And if we do it in radians, well, we're going to say this is 400. And then cosine, oh no, you can't do it. I don't know what cosine, yeah, no. So we'll just do it with, so we got 400 cosine of 9.16 degrees. Alright, so we got 400 minus cosine of theta. Alright, so this one's just really, what am I saying? This is over-exaggeration. I mean, this thing is totally vertical. The curve looks like that, where this is just nothing. You know what I mean? It's a little bit, it's like 1 millimeter. But we got 400 minus that. So we hardly even have 1 millimeter, but we got 0.98 7 millimeters. So that's going to be our value for x. Now, the crazy thing, though, is that's not the value for x. That's the value for x. Well, I mean, yeah, that's why I was just like, this problem was just like, oh, I didn't want to do, I just thought it was going to be easy. But if this was just on a pivot, hell yeah, this would be our x value, and that would be our y value. You know, we would have them. But because this is a wheel that rolls without slipping, whatever it travels during the arc length is also what this origin travels. So now we're going to have to add that to x. So what was the arc length? So arc length was going to be this. What's our equation for arc length? Isn't that well? It's going to be theta times radius times yeah, radians times radius is arc length, something normal. We don't know. Well, I guess we solved for the radians. Yeah, that was going to be 1.6. But how did we get that? So this just, it's also interesting, like how did we get this? Well, we took omega times time. So it's just fascinating to kind of pay attention to that stuff, because sometimes it's just intuitive. That's why I go back to like driving. You know, no one thinks twice of like what you're actually doing, especially this one. Hey, the next town is 60 miles away, and I'm going to drive 60 miles an hour. How long is it going to take me to get there? 60. I mean, it's going to take an hour. But I don't think people think in their head that they're stacking units in kind of a bizarre way. You're taking distance divided by time, and then time pops upstairs. You know what I mean? So this gives you a value, meters cancel, and then you get time. Yeah, so it's just kind of fascinating. Even with radians, it's just like, yeah, anytime you're kind of doing something intuitive, and just take a step back and see what the equation was. So we took radians times time. We took that 1.6 times 0.1 seconds, and this gave us radians. Cool, so that is an equation, you know what I mean? So there you go, we got another equation. Angular speed times time is the angle that we're you know what I mean? That this circle is moving. And so, hey, this is the equation for angle times radius is that arc length. So now we can just say angular speed times time times radius is arc length. But I don't know, I would just never memorize anything like those. But anytime that I guess I'm working with radians, I mean, I would do these from kind of my little memory trick. But then, yeah, kind of work out the other ones. Okay, so the arc length is going to be, because we need to know that, because this arc length is the distance traveled by the center of the circle, which we're going to add to x. So now we can say, even just for an equation for x, heck yeah, you can, you know, anytime you kind of work intuitively forward, go back and just see if you get it all in one step. You know what I mean? So what did we do? We said x is going to be s plus this r minus cosine theta. And then even, what was theta? Theta was omega t. Cool. So now we have x is equal to, and the arc length, how the hell did we find arc length again? That was omega t, what was that? Yes, because arc length is theta r, and theta is omega t. So arc length is omega t r. Yeah, right there. So cool. So we're going to have omega t times the radius plus the radius minus cosine, and then theta is just omega t. And like, I'm even hella tired, and this is the kind of the first time I've ever kind of really done that. But yeah, equations like this, they just don't look good, and you don't know what the hell's going on. But it helps you when you're reading textbooks, because yeah, this term comes up a lot. You kind of see like, hey, cosine omega t or sine omega t for yeah, it's just kind of interesting. All right. So that's going to be let's let's just do it up. So x is equal to 1.6 times 0.1 times 400 plus 400. And you could even factor out this r if you wanted to. But anyway, minus cosine of 1.6 times 0.1. Cool. And we got to be in radians. That's the only thing, because this is in radians. So we need to change our calculator to radians. And we got 1.6 times 0.1 times 400 plus 400 minus cosine. I'm just going to do this one is 0.16. There we go. And so heck yeah. So x. Oh, this seems way the hell wrong. Bummer. What did we do? Whoa. This isn't just cosine. This is r cosine. Yeah, no duh. So yeah, you can totally just factor out the r. But anyway, my bad. And so we have 400. Because what did we say? Hey, if this is the cosine is just the fraction of this hypotenuse. The hypotenuse is the larger number, and we're going to have like 90. We're going to basically have 99%. Like what is cosine of 9 degrees? Whoops, got to switch to degrees. Cosine of 9 degrees. Yeah, it's 98.7%. All right, so what did we get? Yeah, we got 69. Cool. Because our arc length was about 64, and yeah, is that right? Our arc length was 1.1 times 0.1 times 400. Yeah, so our this thing's going to travel 64 millimeters forward, and I don't even know where that is now. Yes, this one, but we got to put 400 in front of it. Okay, so 69 minus 64. So, is that right? Well, would this have been 5 millimeters? I feel like that's not true, but let's figure that out. Alright, so we have, so the generic form for x, yeah, I'm sorry, and I didn't put that r there. Yeah, holy hell. So this, and we're going to factor out the r. So x is r 1 minus cosine theta, and we have 1 minus cosine theta, and then times 400. Whoa, we need to get back to degrees. Sorry about that. So we have cosine of theta, and then 1 minus cosine theta times 400. Yeah, that is 5. Yeah, that's 5 millimeters. So x is 5.1 millimeters. Cool. Okay, but check it out. That's just if this was point A. You know what I mean? And it's not. And so so what we did right there, it's kind of fascinating to do. Like, I always like to do a different problem, because it kind of takes the stress off. For whatever reason, it's just like the second you actually try to do you think you're gonna, like, you know what I mean, mess it up or something. But doing a different problem is just like, who the hell cares? And so we just did that one where, like, hey, this was the location, and when it swept up to there, so it went over just a fraction, about 5 millimeters, and then it went up about hella 63.72, but as it rolls up, this whole thing moves, you know what I mean? So this whole circle moved that way too, so this x also becomes quite large. And what was it? It was 69. So cool. I'm actually going to store that as x, and then we're going to do 63.72. I probably shouldn't be finding this number like this, but there we go. We're going to store that as y. Cool. So those are our two coordinates for where this moved. And so check it out. This is fixed in this axis. And let's see. This is really painful when I'm so tired. But anyway, okay, so let's say this moves this way and this way, just about equal parts. If this just moves straight up, this would move straight up, and this distance would not change. Cool. But if this moves over by this amount, this has to move up, not by the same amount, but just so that this line is the same. So if I move over here, this has to be 1,000. So that's the continuity there. Cool. And but the thing is that if this moves, oh no, never mind. What did I say? I said if this moved up, this would have to move up. Oh, interesting. Yeah. So that's fascinating. So if this moves up, this has to move up. So you can do things in kind of two steps. That's why we do things in like orthogonal directions. You know what I mean? Like one does not influence the other. If we move up, this has to move up. And then it's just like a new problem. So let's do that. And then so you're right there. But then when you move this one over, well, holy Toledo, this one has to move up. But we just maybe don't know how it moves up. But this direction, for sure. So if we say this whole thing moves up 63.72 millimeters, this had to move up the same. But then when we go to move this one then over, then this one's going to move up. Okay, and then like all we're trying to do, I don't even know what we're trying to do, but we're trying to figure out how much it's rotating. So yeah, that's kind of interesting. How do we even do that? Just by these coordinates. Oh yeah, I totally forgot. Yeah. Because okay, check this out. And we probably should get a new sheet of paper. We don't have one. But yeah, so yeah, when this rolls, these things just go up vertically, right? Cool. And then, like I said, nothing changed. Okay, and then this angle stays at 30. You know what I mean? The angle didn't change. But the second this moves in by like that much, this has to move up. And check it out. Our angle gets to be like maybe 31 degrees. Okay, and remember, all this has happened in 1/10 of a second. You know, that's the most important thing about kind of running things for a second or 1/10 of a second. Just get used to like doing it, but then still keeping the problem kind of visual. So now we can say that, hey, we changed our angle. That's the definition of angular speed, is going to be a change in angle divided by a change in time. So if we had a 1 degree, and 1 degree you would have to like divide by 360 degrees and then multiply by 2 pi radians. Hell yeah, degrees would cancel, you get radians. And then you would divide by 0.1 seconds. Alright, hell yeah. So we're back, and I think we should just grab a fresh sheet of paper, because man, we could probably just get there a lot faster. So as this rolls, heck yeah, like more or less, it's going to go vertical, but it's going to have a vertical component, and obviously it's going to move this way. And when it rolls, it's going to do something like that. So yeah, let's maybe solve the problem from this perspective. You know what I mean? So this is going to go like that, and it's going to at A we're going to have a tangential velocity, and so we say omega radians per second times radius is tangential velocity. So our tangential velocity here will be 1.6 times 200. Well, we got to do 0.2 because we got to get keep it in meters per second. So we got 1.6 times 0.2, and we get 0.32 meters per second. That's our tangential velocity. Same thing, we're going to run it for a second. So what did we say? So radians per second times 0.1 seconds. So we have 1.6. Hey, this is going to get our angle. So sometimes I do that, you know what I mean? The units kind of are the equation. And so, hey, this was angle, and this was time, and so, or I'm sorry, this was speed, angular speed times time, and this gives us our angle of 0.16 radians. Alright, sweet. And once we know that, you know what I mean, so we have this angle, and it's exaggerated, but there you go. Now we know our angle, and we can find this component, and we can kind of find the y component and the x component. I mean, actually just this component. We want to know how much we're going that way and that way. And so we say this y is going to be as the radius, so it's 200 millimeters times the sine of 0.16. So I guess we'll just stay in radians now. So 200 sine of 0.16, and we get 31.86 millimeters. And is that what we would expect? 0.16 times 200? Yeah, because radians times radius, you know what I mean? With small angles, radians times radius is the arc length, but with small angles it's also the vertical component. And so this is kind of synonymous with 32 millimeters. Now this one won't be. There's no small angle theorem for the cosine, obviously, because it's but you can just know that it's going to be almost 200. You know, it might be like 199. So x is going to be r minus r cosine theta, or just r1 minus cosine theta, and that's going to be 200 1 minus cosine of 0.16 radians. So we got 1 minus cosine 0.16 times 200. And this thing does move just a little bit. It's 2.55 millimeters. I'm going to store that as x. We're going to store this one as y. So this is x in my calculator. This is y. But like we said, this whole thing has traveled in arc length. And so that was useful to get the tangential velocity out here. So I'm going to say the velocity... I don't know what we would call it, just velocity prime. Velocity tangential prime is omega times r. Radians per second times radius is tangential velocity, so we got 1.6 times 0.4 meters. And that's going to be that 64, it's going to be 0.64 meters per second. And then we're going to run it for a time of 0.1 seconds. Units cancel, and we got 0.064 meters. I don't even think that's what we wanted. What did we want? Did we want that? Yeah, we wanted arc length. So yeah, arc length is angle times the radius. So or radians times radius is arc length. And did we even find radians? Well, I think we had it from up here. There you go. So we got 0.16 radians times radius of 0.4. This is going to give us 64.064. Cool. So 0.064 meters. Yes, so this was the arc length. So yeah, this is the arc length. And then this is 64 millimeters. So what we know about a rolling circle is whatever track it lays down, or, you know what I mean, if it lays down, if it, you know, goes from here to here, laying down that track, this is going to be the new pivot point, and guess what? The center of the circle is going to be right there. Oh, that was pretty sweet. I think that's just a really good visual way to do it. Just be like, hey, like the circle is going to lay down track, and, you know, so if it lays down this track, this is going to be right there. You can very easily see that. And then the new circle, it will have its pivot point. This point will be right there. You can just imagine the circle over here, and guess what? The center is going to be right there. So that means that this, we're going to say like x actual, xa, is going to be whatever x was here plus arc length. And so we have 64 stored as s, as arc length, plus x. And I'm going to store that as xa. So I'm going to say this is 66.55. I'm going to store it as a. So this was the 2.55 plus 64. Cool. And that's what we got right there. Okay. So, and now we can go back to hey, so we said that this thing will go up in the y direction by, what was our y? So yeah, our y was 31.86. So then this point B is going to go up 38.1.6. That's totally independent. You know, if this goes straight up, this has to go straight up. Yep, because, you know, I mean, this length still has to be the same. But the second this one goes in by quite a bit, by like 64, well then this one has to go up. Not the same amount. So this was right here. But now it goes in, and it has to go up by some amount, just so that this is still 1,000. And so that's the triangles that we're going to draw. And we can even draw like this first one. You know what I mean? The first one is going to go up, but it's going to be the same as this. And maybe we just want to know what this distance is. I'm going to call it, I don't know what I'm going to call it. I'll just call it D, distance D. And so, hey, we know our hypotenuse, that's 1,000. Now here's a fast way to do it, you know what I mean? It's always easy to take like this 1,000, and then, hey, the sun is shining on the sinus, so we take it times sine theta, we take 1,000 times cosine theta, and sine and cosine are always going to be fractions, you know what I mean? It's going to be like a fractional number of this 1,000. But if we have... oh yeah, no duh. I was thinking something different. But yeah, that's what we're going to do. So we're just going to take the cosine of 30. Sometimes you have this length and you need to find the hypotenuse. For whatever reason, I was thinking we had that scenario. But we don't. So it's 1,000 times cosine theta. And our angle is 30 degrees. So we have cosine 30. So we have 1,000 times cosine of 30. And I just got to switch back from radians to degrees. Cool. And so we have yeah, what is it the cube, is it the the cubed root of 2 divided by 2? Like what's divided by 2? Like what's I have no idea what this is in radians, 30 degrees. But anyway, well obviously 30 divided by 360 times 2 pi. So I don't know why I was thinking it was a part of a square root. That must be other things. Anyway, so we have 1,000 cosine of 30, and we're going to store that as alpha d. So cool. When we go over, hey, this d changes. We're going to call it alpha e. So then we actually need to find the angle. We would know alpha e, so d minus this alpha a will give us alpha e. So we have alpha d minus alpha a. That's going to give us this length, alpha e. I'm going to store that as e. So now we just know that this length is shorter. Now we want to find our new angle. I'm just going to call this angle w. And so this is the cosine component. So you could just write it out. 1,000 cosine theta is equal to E. How else would you do it? Yeah, it is good to know that just cosine of this angle, like so this has to be a fraction that's less than 1. You know what I mean? So if it's a fraction that's less than 1, the hypotenuse has to be on the bottom. And then because it's cosine, it has to relate this adjacent side. You know what I mean? It's the definition, but I swear it's just like, I don't know, from engineering, I don't know, I don't know if a lot of students actually just go back to this as the basics, because I don't know, maybe it was just me, I just missed the bus on always returning to this. But I just think of it as a fraction, and where the hypotenuse, so if I say cosine of this angle is, heck yeah, that's going to be E divided by 1,000. Oh, but that still doesn't get me what E is. No, it does. No, holy Toledo. But yeah, if I did one step farther, I would just say, hey, this angle, this new angle that I want, has to be inverse cosine, and then that would be E divided by 1,000. Cool, so let's do that. So we have inverse cosine. of alpha E divided by 1,000. And, yep, and so here's our angle, not in radians, it's in degrees, it's 36.9. Okay, so that was pretty significant. So even, I wasn't expecting such a big angle change, but my preconception was that this was not rolling. Yeah, that was fascinating to me. Yeah, I just thought it was like a fixed axis. But no, it's rolling. So that's a huge aspect of this problem. Okay, so now that we have this new angle, we can take and we're going to store that. Yeah, we stored it as W. So we can find the change in the angle. You know what I mean? Because what is omega? The omega, the angular speed of this bar, and just in general angular speed, is change in angle, change in time. And so we just did it. We changed our angle by like 6.92 degrees. Oh, but we need it in radians. Damn it. Okay, so that's cool. We're going to go 6.92. I mean, basically, we're going to have this 36.9 minus 30. And then we're going to maybe divide by 360, multiply by 2 pi radians. Degrees will cancel. We'll have radians, and then we'll divide it by 0.1 seconds. So we're going to have this minus 30 times 2 pi divided by 360 divided by 0.1. Cool. So our angular speed is going to be 1.2 radians per second. All right, and sweet. So now that we did it once, and like this won't be the most accurate if you take something that's like, especially when it's visual. But that was good. You know what I mean? I don't like to, for the first go around, take my change in time to be something that's too small, or it's just I kind of lose any frame of reference for it. Okay, so now what we're going to do is just change that change in time, because we need to kind of back up our answer. Alright, so if we make the change in time 100th of a second, let's see. So here's our angular speed. So we would take 1.6 times 0.01, and we would go this way. So we would have 0.016 radians. Radians times radius gives us our angle. Cool. So we would have 0.16 times 0.2. Yep, so we would multiply by 0.2. That's like 2 times 16, that's going to be 32. But with 1, 2, 3, 4, we got to move this 4 times. So we would have 0.0032, and that gives us radian times radius, gives us, radians times radius. Oh yeah, it gives us the, oh no, what am I doing? We already have the angle. Oh, I'm like really tired. Holy Toledo. Okay, so if we have the angle, we know what y is. Y is going to be 200 sine of 0.016. X is going to be 200 minus 200 times cosine 0.016. And then, but x of a is what we want. That's going to be plus the arc length. I guess that's what we just did, radians times radius. So that's going to be 0.0. Oh, yeah. So radians times radius of 0.2. Oh, radians is dimensionless. So I could just multiply this by 200 to get the arc length in millimeters. Okay. Hey, I'm learning on the fly. That was pretty cool. Yeah, radians is dimensionless. So it's just fascinating dimensionless terms. When I just always think of like converting radians to meters per second, but I've never thought of converting it to millimeters per second. But yeah, no duh. So that's just going to be 32. It's going to be 2 times 16 and then we would move it 1, 2, 3, but just 1. So it would be 3.2. So we would get 3.2 millimeters, and no, would it be 32? Holy Toledo. 1, 2. No, it would just be 3.2. Yeah, we're only going 100th of a second. So yeah, so we're going to add 3.2 millimeters. But this is going to be real small. So we have 200 minus 200 cosine 0.016. We got to be in radians. And yeah, so this is only 0.02 millimeters. So we're going to... Alright, hell yeah, we're back. Yep, so this x, so the distance this way that this travels, basically 3.2, but plus just a tiny bit more. So we're going to have plus 3.2. I'm just going to store this total distance across as x, so that's going to be our xa, or x actual. And then the y, what was y? It was just 200 sine of 0.016. So we're going to store that as y. So yeah, that went up 3 millimeters. Okay, sweet. So still visual. Okay, so our D has not changed. That's 866 millimeters. But now our alpha E has changed. That's going to be this alpha D minus X. Alright, so this is alpha E. And we want the angle. Again, that's just inverse cosine. We can just go for it. And think cosine is just a fraction, between 0 and 1. So it's going to be alpha E divided by 1,000. And this will give us our angle. And yeah, it's the angle in radians too. Cool. But we got to convert 30 to radians. So we're going to have this is in radians, but we got to subtract 30. But 30 divided by 360 times 2 pi. Okay, so this is the difference in radians. So now we have this change in radians, and now we got to divide it by the change in time, 0.01. Cool. So that didn't work at all. Yeah, we get 0.64 radians. Oh, my bad. No. So our big mistake. Yeah, that's why it's good to do it one time and then do it again, because the arc length that I used was wrong. It wasn't on this 400. So this arc length is going to be, what is arc length? Arc length is radians times radius is arc length. Okay, and then we know how many radians we have by 1.6 times time, 0.01. So we have this many radians times our radius, but that's going to be 400. So yeah, so our arc length is 6.4, not 3.2. So we have to go back to this value, 200 minus 200 cosine of 0.016, and then add 6.4. 6.4. So that's going to be our x. Cool. And then alpha D from that last problem minus x is going to start as our alpha E, and then we have inverse cosine of alpha E divided by 1,000. Cool. And now we're going to subtract this 30 divided by 360 pi times 2. See how I did this 30 divided by 360? Now it's only going to do that once. It's not going to divide everything. And then it's just kind of cool. I would have to do times 2 pi. But I can just do pi 2 because it's character. And any letter characters, obviously, they're going to multiply. And it's not just going to add as a number digit like 360 pi 2. But anyway, so sweet. So that's going to be our change in angle divided by 0.01, and we get 1.27 radians per second. Cool. So now we're just going to improve our guess. We'll try to do this one more time just to see if we don't make any errors. Okay, and now let's see if we can just do it intuitively. So I'm going to run this for a thousandth of a second. So we're going to go 1.6 times 0.001. What does this give us? This is going to give us my angle. Cool, I'm going to store that as theta. And I'm going to go my radius, 200, sine theta. I'm going to store that as my alpha y. Now the alpha x, well, we do the x right now, so it's just going to be 200 cosine of theta. But that's not true. That's going to give me that length. So I need to go 200 minus that. So this is why it's just kind of nice to do things just individually, because you really can't mess up. I'm going to store that as alpha x, but I do need, as this thing rolls, how much it rolls. So I do need to find, I know that this angle is going to be 0.0, well, it's going to be 1.6 times a thousandth of a second. So this is my angle, and I think I already had that stored. Angle times radians times radius is arc length, so I'm going to multiply it by 400. So perfect, so we have 0.64. So this x plus 0.64, this will be my new x. Sweet. Now I know what d is, and I mean we can do it again. We can go 30 divided by 360 times 2 pi. This is radians. And I'm going to actually store that angle as u, that initial 30 in radians. So we would say 1,000 times the cosine of my of 30. This is 866. So we have alpha d, so that jives. And alright, hell yeah. So we took a little break, and I totally forget where we were. Oh yeah, we're probably doing that cosine thing. You know what I mean? Inverse cosine of alpha e divided by 1,000. Heck yeah. So now this gives us that new angle. I'm going to store that as w. And so we're going to have alpha w minus this 30 in radians. And so this is my change in radians, and our and you already see it's 0.0127, you know what I mean, so heck yeah. And we're going to divide by 1,000th of a second, and, oh, what the hell, why didn't that work? 12.7 radians. Oh, we messed something up. Alright, let's probably just do this one again. Oh, was this not 6.4? You know, this is probably like 0.64. But anyway, so let's see what we have. So we have our angle. Is this going to be right? 1.6 times 0.001. Okay, it's perfect. That's good. And we're going to go 200 sine of that angle. And then is that alpha y? Yep. And then we have 200 minus 200 cosine of that angle. And that's going to restore that as alpha x. But we have the arc length, so that's going to be the radians times radius, so we have times 400. Yes, it's 0.64, you know what I mean, so I'm just making hella mistakes. But yeah, that'll make all the difference, and then so we're going to add this to that x, and then store that as our total x across. Okay, so now we're going to have this alpha d, this total distance, minus x, and this is alpha e. Store that as alpha e. And so now we're going to have inverse cosine alpha e divided by 1,000. But see how it's just so nice to just do a problem about 3 or 4 times, because then you just get used to it. Doing a problem once is probably the dumbest thing you can do. That's why I always choose an easier problem, then go back and do the actual problem. And then, I mean, we're not even doing the actual problem, but the problem that I want to do. You know, this method is kind of cool. Okay, so I'm going to store that as w, and then we got alpha w minus 30 in radians. Cool. So now divided by 0.001, and heck yeah, we get 1.279, and let's mosey on up here to see what our other one, and see what the difference was. See if it's not up here too far. There we go. So that's going to be the difference, and so our air, you know, so yeah, we're approaching, you know, a better answer each time. So 1.27, so I can just say this is 1.28 radians. And heck yeah. So yeah, this was just 1.27, but running it just a little bit better, we get 1.28. Sweet. And we might as well do it one last time and do 10,000ths of a second. Just because we kind of have this down now. 1.6 times 1 divided by 10,000. You know what I mean? Heck yeah. Store that as theta. Alright, so we have 200 sine theta. Store that as alpha y. We have 200 cosine theta. And then 200 minus that. Store that as alpha x. We're going to have radians times radius, so times 400. 0.064 millimeters. So we're going to add that to x and store it as x. Alright, heck yeah. So now we do alpha d minus x, store that as alpha e, inverse cosine of alpha e divided by 1,000. Store that as alpha w minus alpha u, divide by 1 divided by 10,000. 10,000ths of a second. And we get 1.2799, and we'll compare that to what we had before. Heck yeah. And now, I mean, you could really just do that. You could do 1 divided, you could do 10 to the negative 6. Run this as my time, times 1.6. And I'm going to store that as my theta. You know what I mean? And then I'm going to go 200 sine of theta. I'm going to store that as alpha y. And then 200 minus 200 cosine theta. Store that as x. And then we'll have 10 to the negative 6. That's going to be... times 1 point. Actually, this is my theta. And then radians times radius, so times 400. And then add that to x, store it as x. Sweet. So now we have alpha d minus x, store that as alpha e, inverse cosine, alpha e divided by 1,000. And then we just subtract u, and then divide by 10 to the 6. Cool. And then so this is our answer. No. 10. Sorry. We would divide by 1 divided by 10 to the 6, which is dividing by 10 to the negative 6, which is multiplying by 10 to the 6. Sweet. And we get 1.27999. 1.27999. So this might be approaching 1.28. I'm not quite sure. But let's take a look at the answer in the back of the book and kind of be done with this one. But yeah, it's such a cool method. I really like it. So here we go. So the answer right here is 1.28 radians. So yeah, that's exactly what we were approaching, 1.28. So yeah, pretty cool. But yeah, I have no idea instant centers. See, that's a thing where it's just like, in 10 years, even after learning about instant centers, you'll probably totally forget. You know what I mean? So why not use this method? But I will. I like my method, and then I'm going to go learn what instant centers are and see if I could actually use those. Oh, I see what instant centers are. So what they have is they're saying like, hey, this is a pivot point right there. So that's fascinating. And this brings up an interesting, like circles, like rolling circles are fascinating. They have to be rolling without slipping, and just don't think every circle rolls without slipping, because you could have one that spins out. You know what I mean? Or you could have one that as it's rolling skids, or just one that's a point particle and just kind of like totally just moves sideways. You know what I mean? But with the rolling without slipping, your omega, as if it was around an axle, is the same angular speed of this pivot point. So that is fascinating. The angular speed of the circle is the same as the contact point. The angular rotation of this contact point is also that same speed, 1.6 radians per second. So then... yeah, and that's all I know. And I guess they're taking this line going through here and going through there, and yeah, that's fascinating. I still don't know what they're doing for instant centers. That's gonna be for another video. But hell yeah, so we did it, and I'm hella tired. I'm gonna go to bed. But anyway, that was doing a math problem or physics problem when you're hella tired, I think. So this one's, I don't know if I'll post this or not, but thanks for joining me, and that's a video.